Hello students, myself Dr. Govardhan Edu, Assistant Professor Physics, Government Rajiv Lochan College, Rajim. Today I am deliver a lecture on fiber optics. This is very helpful for the M.Sc Physics students. In the 19th century, the communication system carries information from one place to another place by the traditional copper wires. In the 20th century, the information carrying system changes from copper wire to the fiber. There are many advantages of optical fiber over the copper wires. The fibers get light from the source and transmit the information, whatever may be the information, either it is audio, video, text, data, and mixture of them, can be transmitted from one place to another place by the silica, by the glass, and the speed of light. So we can see that in the communication system, mostly the fiber optics can be used. Not for the communication system in the field of medical, defense, and semiconductor devices, the fiber optics can be used. So today we can discuss about what is fiber, what are the principles of fiber, what are the cross section of the fiber. So let us start. What is fiber? Fiber is a glass or plastic as thin as human hair, and it is designed to guide along the fiber. The principle of fiber optics depends on the total internal reflection, and the optical path of the light along the fiber is zigzag. So in the principle of fiber optics, we can discuss how the light can be accepted by the fiber and how it can be transmitted along the axis of the fiber. So first of all, we can see that the cross-sectional view of the fiber. The innermost part of the fiber is called core. It is a light guiding medium, so the light can be transmitted through the core. The approximate diameter of this core is 50 micrometer. The middle region, which is cover the core, is called cladding, and the diameter of cladding is around 125 micrometer. The main work of cladding is to make light into the core. So the cladding can be confined the light into the core. The outermost region is called sheath, and the diameter is approximately 150 micrometer, and the main work of sheath is to protect core and cladding from the external influences. So the fiber optics makes a good, flexible, and available source of communication system. So let us now discuss about the principle of fiber optics. The main function of fiber optics is to accept as much light as from the source as possible. The fiber optics can be depends namely on the core size and the numerical aperture. And the numerical aperture of the fiber optics can be determined by the acceptance angle and the fractional refractive index change. The quantity, numerical aperture, acceptance angle, and fractional refractive index change can be discussed later. So here, this is the diagram of the transmission of light or information through the fiber. Let us see how it can be explained. Here this is the region of core where the refractive index N1 is denoted here for the core. So the refractive index of core is N1 and the middle coaxial is the cladding. Here the N2 is the refractive index of cladding. In the transmission of light through the fiber, the refractive index of core should be greater than the refractive index of the cladding. And this is the axis of the fiber, and this is the launching zone where light can be launched from source to the fiber, and this is the theta angle. Theta is the incident angle which makes the incident ray and the axis of the fiber. So the incident angle can be made by the fiber axis and the incident ray. Here the N0 is the refractive index of the launching zone. Generally the launching zone is air, so the value of N0 is 1 for the air medium. When the light is launched into the fiber, firstly the light get refract from the point A and it undergo to the core cladding interface point. Here B is the core cladding interface point and theta r is the refracted angle. So theta r is called reflected ray. This is reflected ray and theta is the reflected angle. So the light goes from N0 refractive index to N1 refractive index when at the core cladding interface point the refracted ray becomes incident ray for the core to cladding point. Here when the phi is greater than the critical angle, let us assume that phi c is the critical angle at the point B. So the phi is greater than equal to phi c, light is rebound into the fiber and propagate along the axis of the fiber, and total internally reflected ray can be obtained. So the incident ray from the launching zone to the core is here, but the incident ray for the core to cladding is A to B, and at that point B the incident angle, suppose phi is the incident angle at the core cladding point, this becomes greater than phi c. Phi c is the critical angle at the point B. Then light is totally internally reflected and propagate along the axis of the fiber. So there are two interface points in this section. So here point A and point B is the two interface point. So in those points we can apply the Snell law because there is a change of refractive index N0 to N1 and N1 to N2. So we can write from the Snell law sin theta I upon sin theta r is equal to N1 by N0. This is the Snell law for the two mediums where the refractive index are different. Here N0 and N1. That means the Snell law can apply in between launching zone and core. So we can write sin theta I is equal to N1 by N0 sin theta r. Now we can see that in this section. Let us see in broader way. This is the actual considered region in the core and cladding interface. This is theta, this is phi, and this is 90 degree. So in triangle ABC, we can write theta r plus phi plus 90 is equal to 180 degree. So we can calculate the value of theta r. So theta r is equal to phi 90 minus phi. We can put the value of theta r into in this equation. We get sin theta I is equal to n1 by n2 n1 by n0 sin of 90 minus phi. Now let us consider when the theta is the maximum. When the theta is the maximum, then phi should be greater than or equal to phi c. So when we consider the maximum theta I, which is called acceptance angle in fiber optics, which is discussed in later. So now consider sin of maximum theta I is equal to n1 by n0 sin of 90 minus phi c. Here we can write maximum of theta I, then here we will write phi to phi c. So this equation becomes n1 by n0 cos of phi c. Using the trigonometric properties, again we can apply the Snell law in the core cladding interface point B. Here at the point B, sin phi c is equal to n2 by n1. So the value of sin maximum theta I is equal to n1 by n2 cos phi. The cos phi is converted into sin phi, then we get the another equation n1 by n0 and cos phi is equal to root over n1 square minus n2 square by n1, because cos phi c is equal to root over 1 minus sin square phi c. The value of sin phi c is n2 by n1, so we get cos phi is equal to root over n1 square minus n2 square by n1. So the value of sin maximum theta I is equal to root over n1 square minus n2 square bata n0 sin of maximum theta I. This is the desired equation for the fiber optics. As we said earlier, the main function of the fiber is to accept as much light as possible from the source. So the sin of maximum theta I is the possible light which can be accepted by the fiber and transmitted by the fiber along the axis of that. So sin of maximum theta I is called numerical aperture. This is numerical aperture. So the numerical aperture can be defined as the maximum acceptance angle by the fiber. Or in another way, the numerical aperture can also be defined as the light getting ability of the fiber. And the mathematical equation for the Na is root over n1 square minus n2 square upon n0. And it can also be written as Na is equal to root over n1 square minus n2 square, because in general the launching zone refractive index taken as 1, because launching zone generally taken as the air. So, and the maximum theta here, now we can see that the value of maximum theta is called acceptance angle, and which is equal to sine inverse root over n1 square minus n2 square upon n0. So the maximum theta is called acceptance angle. Acceptance angle can be defined as the maximum angle where light can be relative to the axis of the fiber and propagate along the fiber. And we can see that theta I is propagated, the incident angle is propagated in a zigzag path within the fiber, when the total internally reflection condition can be hold each and every core cladding interface point. Here the B is core cladding interface point, here another core cladding interface point. In each of the core cladding interface points, the maximum theta I has the value phi greater than equal to phi c. So the each and every time the incident ray cross the axis of the fiber, that means it is relative each and every time through the propagation. So the maximum theta I is the acceptance angle when and which the light ray can every time relative to the axis of the fiber and cross the axis of the fiber through the propagation of fiber. And the 2 times maximum theta I is called acceptance cone. The light ray contain a cone having full angle to 2 theta I that can be accepted by the fiber and transmitted by the fiber is called acceptance cone. Again we can repeat, the maximum light contained within the cone having angle 2 theta I accepted and transmitted through the fiber is called acceptance cone. So this is the principle of fiber optics. From that we can define numerical aperture, acceptance angle, acceptance cone. Now we can see that del. This is the fractional refractive index change. So del is equal to n1 minus n2 by n1. This is the definition of del fractional refractive index change. It is normally the difference between the refractive indices of core and cladding. The main condition of the fiber optics is the refractive index of core is always greater than the refractive index of cladding. And the value of numerical aperture can also be calculated by the other equation. Now we can manipulate the desired numerical aperture equation, root over n1 square minus n2 square. Now we can write n1 square minus n2 square is equal to n1 plus n2 and n1 minus n2. Now we can write 2n1 in denominator and multiply 2n1 in numerator, and the parameter n1 plus n2 by 2 equivalent to n1, and n1 minus n2 divided by n1 is denoted as del, as we said earlier. Del is the fraction reflection exchange. So the value of n1 square minus n2 square, n1 square minus n2 square is equal to n1 plus n2 by 2 is denoted as n1, n1 minus n2 denoted as del into 2n1. So 2n1 square into del, n1 square minus n2 square is equal to n1 square del. So numerical aperture is equal to root over n1 square minus n2 square is equal to 2 n1 root over 2 del. So this is the another way of writing numerical aperture of the fiber. So now we can conclude that in the fiber optics, fiber is made of silica, glass. It is abundant in our atmosphere. We can easily achieve the sand, silica from the nature. So in the plastic or glass, light can be guided. That is the very interesting features. And the velocity of light, as we know that per second 3 lakh kilometers can be traveled. So the light guiding medium is the glass, silica, and the information is in the form of light that can be transmitted from one place to another place. So this is the very fast and non-destructive, non-deradiated method for transmission from the information from one place to another place. Here we can calculate the physical parameter of the optical fiber, like numerical aperture, refractance angle, refractance cone, fraction reflectance exchange, and so on. Thank you very much.